give me 5 minutes? How does it work?
I'll give you 5 minutes is what people are doing. So
okay.
In principle, it's 5 minutes for questions. So I can give you an earlier warning if you
okay.
like.
So you want to give me a warning at 20 minutes?
Sure.
I know it's more or less 5 minutes.
Sure.
Okay, excellent. Yeah, thanks. Oui, oui, ça marche. Donc, ils ont ça. Ça appartient à Carnegie, ça aussi. Donc, tu branches et ça aussi. Ouais. C'est un Mac que tu as ouais. Donc, c'est pareil. Si tu veux, j'ai même le chargeur. Ah, ok. Il n'y a que le chargeur computer que j'ai avant. Sinon, tout ça, ça. Ouais, non, ok.
Okay. Welcome back to the next session. Can you hear me? Is this working? My name is Henry Krakauer from the College of William & Mary. We have 3 invited speakers this session. The first talk will be given by Laurent Balèche, and the title is Atomistic Simulations of Complex Problems in Ferroelectrics.
Thank you. Thank you, Henry. So as Henry said, I'm going to talk today about atomistic simulations of complex problems in ferroelectrics. This study was done in collaboration with quite a lot of people and different countries and different continents. In fact, there is Abdullah Barakati from Al-Qura University in Saudi Arabia, Simon Fraser University in Canada, Central Supélec in France, Academy of Science of Czech Republic, Xian Jiaotong in China, and also Lawrence Berkeley National Lab. So how to start this talk? This talk starts, in fact, from looking at the experimental literatures, and you can see, in this literature that there are a lot of very interesting effects, but when you look at them, they are really extremely challenging to model or to mimic. For instance, there is a beautiful experiment done by Nina Balke and collaborators some years ago, and what they look at the IV curve of a Bfo system, the Bfo system, which is very peculiar in the sense that it has electrical vortices. And what they found is quite intriguing. In this IV curve, you see that it starts at 1 volt, while if you look at Bfo bulk or made of domain walls, then the IV curves will start here at 3 volts. So you lose somehow 2 voltage in that process. So this is very intriguing effect, and it would be extremely interesting to understand what causes it. It's really quite a phenomenal decrease. But if you think, okay, if I want to do that, to model that, what are the challenges that you have to face? For instance, you need to mimic a very large complex system because you have these electrical vortices, and you need quite a large scales to mimic them. But on top of that, that's not it. You also need to mimic the electronic properties of this large system. For example, you cannot use DFT, the size is too large, and you cannot use anti-atomic potential of bond valence model or effective Hamiltonian because there is no electrons as degrees of freedom, only ions. Another example of very interesting problems that you can find in the experimental literatures, it's about these relaxers of ferroelectrics. I found them extremely fascinating system, and they exhibit quite anomalous properties. For example, if you look at the dielectric response versus temperatures, it really depends how you do the measurement. You can do a field-cool measurement. In that case, you get a plateau at low temperatures, or you can do a zero field-cool, and you get a peak. And even below this peak, there is no phase transition. But there is something that I've been extremely fascinated since I saw it the first time in 1998, and this is this dielectric relaxation. So what it is, if you look at the real part of a dielectric response versus temperatures, it really depends how you are the frequency of the applied field. You see the peak is going towards higher temperature as you increase this frequency. So imagine that we have a dream. We want to mimic the atomistic simulations, this dielectric relaxation. What do you have to overcome? Quite a big things, in fact, because you need a large-scale scheme, because these systems are quite complex. They're usually a disorder, so you need quite a lot of atoms to put into the supercell. You also need to have a model that is able to capture the complexity of relaxers, what drives it, and also you need to incorporate effects that are not that easy to incorporate with usual DFT calculations, let's say finite temperature, but also frequency effect. So what I want to do today, if time allows, is to show you that nowadays it's possible, in fact, to tackle these problems with atomistic simulations. Not only you can tackle them, but also you can learn from them quite a few informations. So this is what I would like to do today. And if time allows, I will divide this talk into 3 parts. The first part is about electronic properties of electrical vortices. The second part is about dielectric relaxations in a lead-free system, which is by Strontium Titanate. And the third part, which is in fact what the organizer asked me to talk about more than the others, but I'm probably focused a little bit more on part 2. This third part is about effective Hamiltonian of PMN. So let me go to the first part of this talk, which is about these electronic properties of electrical vortices. Really, the person that did all this work is Zhigang Gui, who graduated, extremely bright student, and is now a postdoc in Delaware, and we collaborated with a very good friend, Lin Wang. We were postdoc together 20 years ago in Colorado. So let me start again from this extremely beautiful picture by Nina Balke and collaborators. It's published some years ago. I'm also a co-author of this paper, and once again I want to attract your attention to the fact it's an IV curve, and this is for system possessing electrical vortices. It starts at 1 volt. In Bfo bulk, this IV curve starts at 3 volt. So if you think in terms of semiconductor physics, this looks like a p-n junctions, and when does the IV curve start in a p-n junction? It starts at the band gap. So when you first see this picture, you have the feeling that somehow when the electrical vortices form, the band gap has decreased from 3 electron volt to 1 electron volt. Incredibly a dramatic effect. Perhaps there is another solution for this huge decrease, is that perhaps it's not an intrinsic effect, it's governed by defect. So this is what we wanted to tackle, to have an idea. What does this electrical vortices do on electronic band gap? And for that, we are going to consider a very specific type of system, not Bfo, but something else. And why we consider that, and what are they first? They are basically biome titanate nanowires, indicated here, embedded in a strontium titanium matrix. So why we consider this kind of nanostructures is because below a certain temperature, that we are going to call that T-Tor today, you have the formation of electrical vortices. Okay, so above this transition, no vortex. Below this transition, there is a vortex forming. So for example, if you take a snapshot of the dipole configurations, that basically what we call the PT phase, which is when there is no vortex, basically this is how it looks like. The dipoles are basically randomly oriented, and in this red area, this is biome titanate wires, and the green is STO matrix. And here, when you go to this ferroelectric phase, for which you have a vortex, you can see nicely this vortex inside the nanowire. So the idea is very simple to say, but quite difficult to implement. The idea is, okay, let's compute the electronic structure in this phase, in this ferroelectric phase. Let's compute the electronic structure in this phase, for which you have vortex. You compare the two of them, then you will have an idea if, when you have electrical vortex, you can modify or not, quite a lot, your electronic properties. Okay, how do we do that? As I told you before, it's impossible to do by DFT, to be, and you cannot do that by effective Hamiltonian, for example, alone, because there is no electrons. So what we needed to do, in fact, is to combine two techniques to create a large-scale ab initio method. The first idea is quite simple. We're going to use effective Hamiltonian, and what we get from this effective Hamiltonian is basically the ionic configuration. So you get your electrical vortex pattern. Then when you have these patterns, you feed into a code that was developed by Lin Wang at Berkeley lab, which is a DFT code. It's an order n method. This is called linear scale three-dimensional fragment. Very bright original idea from Lin Wang. It's basically technically done by doing charge patching method. So here you calculate the ionic configuration, you feed into this part, and these parts, once you have this configuration, you can calculate the electrical or electronic properties. So this linear scale three-dimensional fragment method has been applied to a lot of systems, especially semiconductors, and lately about this hybrid perovskite, but to my knowledge, it was never applied before to ferroelectrics, so we want to be sure if it can work or not. So what do? We basically do a conventional DFT, 5-atom biome titanate bulk. We calculate the connection band minimum, the valence band maximum. We get these values, and we apply this linear scale three-dimensional fragment with the 3,000 atoms, and basically you get a shift of CVM or VM by a tiny amount, 0.02 EV. In fact, you get exactly the same band gap that in a standard DFT. So we can trust this method. So if we can trust, let us apply for what we are really interested to look at. It's basically, we're going to look at the local density of states versus energy in this PT phase when there is no vortex, and in this FT phase, ferroelectric phase, for which you have vortex. So what does this graph tell us? It tells us basically that the valence band maximum state is formed by, as we know, oxygen 2p electrons, and you have vortex or not vortex, it's the same story. Okay? And what I forgot to tell you is that by black line, this is the STO regions, and this dash red line is in this biome titanate nanowires. So no effect on the valence band. If you look at the conduction band minimum, we know it's due to hybridization between titanium 3D mostly and oxygen 2p. And you see, in fact, when vortex forms, when you go from here to here, in fact, the conduction band edge is pushed up. Okay? So when vortex forms, and by quite a significant amount, 0.25 electron volt. And why is that? It's because now, I think we also saw that in the paper of Andrew Rapp's group, but it's also indicated in this nice paper, is that basically your conduction band edge state is completely governed by this titanium-oxygen-titanium angle. The further away you are from 180 degrees, the further you push up the conduction band state. And this is what's happening. You have 178 degrees in this PT phase and 171 degrees in the FT phase. So that's why when electrical vortices form, the angle gets deviated more from this ideal 180 degrees, and then the conduction band edge state is pushed up. In fact, to see really the result, I think it's probably better to take a look at these schematizations. So this is schematization of the energy levels in this PT phase, no vortex, and in FT phase, electrical vortices are formed there. And in green, this is what's going on in the STO matrix, and in red, these are the levels in the BTO nanowires. So here, when you don't have vortex forming, you have the VBM, valence band maximum, localized in the BTO nanowires, and you have a conduction band minimum also localized in these BTO nanowires, and the DFT value is 1.87 electron volt. And you see VBM and CBM at the same place in the nanowires. We have what is known in semiconductor physics as a type 1 band alignment. But now when electrical vortices form, as I told you before, this conduction band edge state of biome titanium wires is pushed up. And the resultant CBM, conduction band minimum, is now in the STO matrix, while the VBM is in the biome titanium nanowires. So what you have, in fact, if you look at numbers, you have 1.90 electron volt and 1.87 electron volt here. So what these calculations are showing us is when electrical vortices form, you do not decrease your band gap. In fact, you tend to increase slightly the band gap. So probably the experiment of Nina and collaborators, I'm guessing that it's more due to extrinsic defect, but intrinsic effect due to electrical vortices. But what is also quite interesting in terms of semiconductor physics usually is you see that when there is no vortex, it's a type 1 band alignment, VBM and CBM at the same place in these nanowires. But here, when you have electrical vortices forming, it's not the same place. The VBM is on BTO, and the CBM is on STO. This is known as a type 2 band alignment. This is quite interesting because we are talking about the same material. In semiconductors, if you look at one material, it's either type 1 or type 2. You cannot have both. At least I don't know any example of that. But here, what's happening, in the same material, you control your band alignment. You go from type 1 to type 2. And how do you do that? By temperature, which means by formation of a topological defect, which is your electrical vortices. So you have control of a band alignment via topology, via topological defect. This is about the first part of the talk. Let me go to this second part of the talk. And here I really have to indicate that Dawei Wang has done a lot of work. Alexei Bokov, who is here, also was instrumental to understand what's going on with Zhuo Gangye and Yeka Linka. Extremely nice interaction, and I really learned a lot from the discussion with all of them. So what we want to shoot is quite provocative. We want to see dielectric relaxation now with atomistic simulations. And we're going to look at biome zirconate titanate system. It's a lead-free relaxers. And a lot of experiments have been done, or some experiments have been done on that. And we choose this one because we have done already some calculations on them some years ago. And what we found in these systems is basically these polar nanoregions. For example, at low temperature, this is a snapshot of your system. The blue arrows are basically titanium-centered dipoles, and the red arrows are zirconium-centered dipoles. And you see there are some regions, titanium-rich regions, for which the dipoles from parallel to each other, and from one region to another, they are opposite, or at least forming an angle. So you have these so-called polar nanoregions. And here, for BZT, I will show you it's not the case for PMN. They are basically, you have a paraelectric matrix, which is zirconium rich. Okay, what do we do with this system? What we're going to do, unlike the previous study I told you about, we're going to put effective tangent, but we're going to use it in molecular dynamics, not in Monte Carlo simulations. The beauty of molecular dynamics is you can get, let's say, the time dependency of your total electric dipoles, okay, or your polarization. You compute the correlations between the dipole at time t and time 0. You do a Fourier transform, and what you get, it's the beauty of statistical mechanics, you get the dielectric response, the complex one, so real part and imaginary part, versus frequency. This, we can get it quite easily with molecular dynamics. What is quite interesting is how to analyze the data, and this took us a long time. I will say at least 1 year, 1 year and a half, and the solutions, in fact, was provided also by discussion with Alex Zurgon and Jirka. They told us, okay, let's do like an experiment. What does it mean? It means your data, you are going to feed them by a sum of standard empirical functions. Okay? And here we have 4 functions. This one is a little bit complex one. It's called a Breuiliac-Negami, HN for in short. And this is basically a relaxation mechanism. It's a complicated one, and in our case, we found that it applies for the titanium sublattice. You have a second part of this total dielectric response, is basically a coupled oscillator relaxer. Let's call that COR to be short also. It's also a relaxation mechanism, and we also find it in that case, it's for titanium ions. And then you have these 2 parts here. These are the normal damped harmonic oscillators. They basically characterize titanium and zirconium phonons. Okay, let's look at how it looks like. So this is basically the imaginary part of a dielectric response at 150 Kelvin versus frequency. These blue dots here that are moving quite a lot are the MD data. And the triangle here and the black lines are basically experimental results. And the agreement between this blue MD data and the experiment is not bad at all, especially since but in fact, this spectra depends tremendously on temperature. If you are moving a little bit the temperature, the spectra is changing dramatically, and you can see it's not bad agreement at all, except you have to be careful at low frequency, you cannot mimic well the experiment, you are too low for MD data. But the important thing also is, as I told you before, what we are going to analyze, in fact, is not the MD data per se, it's the fit. It's the fit that is super important to understand the physics, and the fit by this empirical sum I'm putting here by a red light, okay, and you see that it fits very nicely into the MD data. But the nice thing is this fit has 4 components, and we can decompose. We can look at these 4 components. For instance, you see the green line, which is here. This is basically coming from these HN functions. This happens, it's really good for low frequency. It's important at low frequency. You have the COR, which is the blue line here, which is important to describe the spectrum at medium frequency. And if you go to higher frequency, it's basically the phonon parts that you are describing. I want to take a look really at these HN functions, because the physics of a relaxer seems to be there, in fact. And in these HN functions, basically, you have quite a few parameters, but 2 of them are quite important. The first one is what is known as alpha parameter. So here I'm showing you alpha parameter versus temperatures, and you see that when you go from high temperature to this T star, one of the critical temperature of relaxers, this is basically 0. 0 means you have a debye. It's a normal debye you are playing with. But as soon as you reach this T star, you see it begins to increase. And to go to quite big numbers, you are not talking about a single debye, you are talking basically about a distribution of debye below this T star. This means it's like the polar region interacting with each other, and they form quite a complex relaxation mechanism. You can also look at another parameters of this HN function. This is known as the relaxation frequency, and you can see that above a certain temperature, which is basically more or less the freezing temperature, except you have to be very careful with freezing temperature in BZT, it follows this quite nice line. This is an Arrhenius fit, and in experiment it is well known that basically you have some relaxation mode in BZT that do follow Arrhenius behavior. And now the next one is what I've been dreaming to see for years, since 1998. It's basically about this dielectric relaxation. I told you before we fit in, so what we have is for each temperature with this fit, we have a dielectric response versus frequency, but we can do the other way around. Now we are going to fix basically the frequency, and we are going to look at the dielectric response versus a temperature. And this is what the data looks like. This is the real part. This is the manager part versus a temperature. This is not an experiment. This is an atomistic calculations. You do see, 5 minutes? 10 minutes, perfect. You do see, for example, that the dielectric response depends on your frequency. And as you increase the frequency, it's going down, the maximum, and it's shifted towards the right side. There's also a nice thing that Alex pointed out. We say, okay, you should also look at the imaginary part of a dielectric response, because there is a relaxation which is a little bit different than the real part relaxation. In particular, if you look at the low temperature, it should not depend too much on frequency. This is what we found. This is known as the constant loss behavior in relaxers. So what I want really to indicate is that now it is possible, via atomistic simulations, to finally get this dielectric relaxation. Also, we wanted we also compare our MD fit or MD data at 0 frequency, the red line, with what you can get from MC result. It's a different techniques to get that. This is indicated by dots, and basically the two curves agree well. So, which means that basically we are quite confident that the two schemes are working well, and we mimic quite well the relaxer behavior. As I told you before, we not only wanted to see the dielectric relaxation, we wanted to have an idea what causes it and if we can further understand it. And in fact, a real beauty of simulations is, you can realize it by looking at the formula of this dielectric response. As I told you here, this is basically an autocorrelation function between total dipole at site 0 and total dipole at time t. But in BZT, there are two contributions of a total dipole, something coming from titanium sublattice and something coming from zirconium sublattice. So in the total response, you have three parts. You have a titanium part, which is indicated here. You have a titanium-zirconium part here, and zirconium-zirconium. What I'm saying is that basically, thanks to simulations, this is something you cannot do in experiment, of course, is you can decompose your total response into atomistic or atomic characteristic. And what this decomposition is telling you is basically what causes the relaxation is titanium-titanium. Zirconium-zirconium, it's basically doesn't depend on frequency, it's a small value. Titanium-titanium, it's the largest value, and this is really when you see the dependency on frequency, and titanium-zirconium is a small dependency with frequency, and this is absolutely consistent with the fact that polar nanoregions in biome zirconium titanate are basically made of titanium-rich regions. And of course, what you can do is something else. You can also look at the temperature Tmax at which the real part of the dielectric response is maximum versus frequency. We do that for two different things. The total response, it is indicated here by blue circles, and the titanium response, I don't know if you can see that, titanium-titanium response, it's indicated here by this dark line. Let me focus on titanium-titanium response. You see that there is data going through it. This data is basically a Vogel-Fischer fit, and what you have, if we look at titanium-titanium sublattice, response is a complete Vogel-Fischer relation. It's very interesting because Arrhenius. For example, the HN frequency is Arrhenius, but the TM is Vogel-Fischer. But if you look at the total response, which is indicated here, you have two parts. For low frequency, is basically one Vogel-Fischer, the same by titanium, but for higher frequency, you have a second Vogel-Fischer for titanium for total response. This is because titanium response begins to be smaller, and titanium zirconium begins to be more consequent. With that, I go to the third part of the talk, which is about this elusive PMN. Why I say elusive? Because you can see the first author is Abdullah Al-Barakati. We started this study when Abdullah was a graduate student in Arkansas, and he graduated in 2004. So it's already 12 years. And every time we are discussing, I'm not happy with this effective Hamiltonian, so we continue to improve. And now we're quite happy with it. I mean, Sergei Prosandev was really instrumental to make this effective Hamiltonian work, and Ibrahim Dekil, who is here, also helped us a lot to understand what is known in experimental literature of PMN. So let me show you the results, some results of them, dielectric response versus temperature. And so what we see this dielectric peak, but what we found is basically below this temperature, it's still paraelectric. If you look at the inverse dielectric response, it's going to show you that below the Burns temperature, around 600 K in the simulations, and not too far away in the experiments, basically you deviate, so you have this Burns temperature. And there's another thing that is well known in the experiment that we wanted to check if we can model it, is basically you can cool your PMN under a field, and so you create the polarization, you remove the field, the polarization stays, and now you increase the temperature, and you see the polarization is going down, and suddenly, a jump. And this is something known in experiment. This is known as the depolarizing temperature, and we found around 250 Kelvin, and experimentally it's probably around 217 Kelvin. The beauty of simulations, you can play with some parameters, and for instance, we switch off what is known as the random field, and these data are basically telling you if you switch off the random field in PMN, you basically get a strong ferroelectric state. So if there will be no random field in PMN, the system will be ferroelectric at 600 Kelvin. We also look at other things, in particular, which is basically a correlation between dipoles. One important thing to realize is the blue color. The blue color is basically about anti-correlation. So if you have dipole here, basically blue color is telling you that other dipoles will be antiparallel to that. And we have these anti-correlations that we found. And depending on the correction you use, and what we found, you can do also Fourier transform of a dipole. And they're going to tell you that when you arrive at T star basically in PMN around 400 Kelvin, you are going to have modes that are not zone center, that are not at zone border, but in between, for which you have a condensation. And you have condensation, not one, but several ones, which explain why you maintain the cubic symmetry, and you don't go, for example, to a tetragonal symmetry. So what we found, in fact, the major player in PMN are random electric field, short-range interaction, and competition between ferroelectricity and antiferroelectricity. And we can take also a look at the local structures. And a nice thing, I was happy to see that the group of Andrew and Ilya now see this polar region as well. And what is very interesting in PMN is that basically they are quite large and they touch each other. It's completely different from BZT, for which they are small and isolated inside a paraelectric matrix. And we did find, I think it's consistent with experiment, but they can increase inside slightly. So let me go. Let me go to the conclusions here. And so that now, with atomistic techniques, I hope I convince you that you can treat quite complex phenomena, things that we can only dream years ago to accomplish. For instance, now we can mimic electronic properties of electrical vortices, combining effective Hamiltonian with order n methods. And what we found, for instance, when you have electrical vortices, you do not decrease your band gap, it increases a little bit. But what is very interesting is you have a control of band alignment via a topological defect. For the first time, I think, dielectric relaxation can be now modeled in relaxers at an atomistic level, and we can understand what's going on inside the system by decomposing. We also can mimic PMN relaxers, and something really that I want to pay attention, because sometimes when you go to a relaxer conference, or when you deal with reports, there's a big fight always going on. I don't think the fight should exist, because what we found is that PMN and BZT are both relaxers, but for completely different reasons. For instance, PMN is very important to have a random electric field. This is not true for BZT. You have short-range interactions that are important both for PMN and BZT. You have a competition between ferroelectricity and antiferroelectricity in PMN, but not in BZT. And the local structure is quite different between these two systems. BZT is small, isolated polar regions. PMN are basically large, touching polar regions. So this is very interesting. You can have two systems that are relaxers, BZT and PMN, but not at all for the same reason. So if you look inside the system, you understand that they can be different, even if they produce the same macroscopic properties. With that, I would like to thank very much the organizer for this opportunity, and thank you very much for your attention.
Thank you, Laurent. I think we have time for maybe a couple of questions.
Maybe I could. You mentioned that in BZT, the relaxation frequency follows Arrhenius' law. And so my question is, can we call it still a relaxor? Because if there is just Arrhenius, there is no freezing.
It's a good question. This one, I don't know if I have I may have a picture here. No, I have only a 10K. But if I look, for example, above 20K, it's true. I have a different picture. It's not a complete freezing. You don't have a real freezing temperature in BZT. That's true. But, so it depends what you call relaxers. But what I will call relaxer now is, do you have dielectric relaxation or not? In BZT, you know you have dielectric relaxation, I mean, from your group in Prague. Experiment theory shows you that. So for me, we can still call them relaxers, but I agree with you. It's BZT and PMN, they're very different. Even Arrhenius versus Vogel-Fischer for the frequency. Yeah,
okay,
absolutely.
I think we'll take one more question to stay on time.
Yeah, I'm curious why you limit the size of polar nanoregions by 2 Lesser-Moe-line dipoles. Why not make one more step?
I don't impose anything.
Yeah, but on the drawings.
Absolutely. This is a very good question. It's a misleading drawing because I'm doing a 2D. Well, when I draw, this is a 2D drawing, of course, but when I do that, I do a 3D. So, for instance, the perpendicular component of this guy is not the same as that one.
I'm not talking about this one. When you draw the distribution of nanoregion size as a function of temperature, it goes
for PMN?
Well, I'm amazed.
For PMN, right? This one?
Yeah.
Yes. So you see there is quite a large error, but you have to be a little bit careful. Of course, we are limiting by the size of the calculations. So we can do.
Why not to use polar nanoregions of one?
Okay.
Why limit by 2?
No, if I go, because one, I don't know, I can say it's parallel to itself, but it's a little bit strange. Yeah,
okay,
yeah, that's true.
We can continue this 1 or 2 discussion in the break. So thank you. Let's thank the speaker once more. So the next talk will be given by Petro Maximovich. To switch or not to switch, another probe microscopy perspective.
You want me to give you a 10-minute warning?
Yes, please.
And then
And then 5.
and 5 is
Right.
actually the end of
The
the talk.
cutoff, yeah.
Because 5 minutes of questions.
Very good. Right, very good. Good afternoon, everyone. It's a great pleasure to be here. I'd like to thank the organizers for generous opportunity to present our recent results on sort of going deeper down the rabbit hole of Mediated response force microscopy. So the title of my talk is a little bit existential. probably by design, because we've been struggling with, not necessarily struggling, but curious about this question, and hopefully you'll understand what constants in a bit. So, but I'd like to get everybody set up for piezo response force microscopy. So let me just start pretty movies made by Steve and Jesse. So what we're interested in, and what I think most people using piezo response force microscopy are interested in, is figuring out the relationship between tip vibration or tip motion and some piezoelectric or ferroelectric properties. And so traditionally, PFM has been a very successful technique to explore the main structure of very well-known ferroelectric materials such as PZT, barium titanate, and whatnot. And the modality has been primarily imaging. And the second modality, which evolved over the last probably 15 years, was local ferroelectric hysteresis, where we are not only looking at the domain structure, but also trying to switch it and understand the relationship of this hysteresis to the microscopic hysteretic properties, distribution of defects, and whatnot. Actually, PFM has been very successful and fairly deterministic technique with few questions asked, so to speak, until about 5 or 6 years ago, when this ferroelectric hysteresis loop started occurring in a whole range of materials, some of which are probably not ferroelectric. And so this work was somewhat stimulated by looking at ultra-thin materials, which are pushing against the size effect of ferroelectricity, such as ultra-thin BTO, sort of incipient or suspected ferroelectrics, maybe strontium titanate, but even things like LiOSTO, antimony sulfide, zinc oxide, and here, aortic walls, right? So basically, PFM has, as a litmus test, started to give some interesting false positives. And we realized this early on, and in 2012, I gave my first probe microscopy perspective on this topic, saying that basically standard PFM methodology is not quite sufficient to evaluate the weak or suspected ferroelectrics, and we have to do something else about it. At the time, and we're still very interested in this, as you'll see in the end, we also sort of surmised that something like PFM should work on ionic materials, and we painted a fairly dark picture, maybe, that if you consider the effect of electric field on material properties, ferroelectricity is somewhere here where things are fully reversible and fatigueless, let's put it like that, and you can go all the way up to material damage and deposition and substrate damage and whatnot. And it seems to be that we have a serious problem in some of these materials, and how to differentiate between various behaviors is not so clear. So today's perspective is actually very happy in this sense, because this is really the last slide I could give in the talk, is that we think we found a very simple approach how to go around that map, and primarily it is utilizing PFM, or now it's PFM in quotes, as you'll see in a minute, within applied electric field, and really looking at the properties of the material as a function of electric field, rather than just looking at a remnant response, which is sort of a very traditional, considered to be non-invasive approach to doing this. Okay, and so today I'm going to talk about 3 topics. The first one is quantitative measurement of contact electrostatics. Second is spatial mapping of dielectric tunability in BST. And the third one is strong emergent evidence of ionically mediated hysteresis, which we have been looking at for a good many years by now. So I'd like to acknowledge the help of my colleagues, and really this work was experimentally primarily done by Nina Balke, and then myself and Sasha have been the role of taken the role of provocateurs or instigators, trying to challenge the signal and the notions behind the signal, and so eventually we developed some deterministic approaches how to go around the various signal modalities. And of course, Sergey and Steven, who always inspire us to do better. So let me start with the first topic, which is contact electrostatics, and this is really to switch or not to switch, right? So what you see is 2 materials, or PFM images of 2 materials, PZT on the left, and then thin film of hafnium dioxide and silicon. There's probably little doubt that hafnium dioxide is not ferroelectric, but you wouldn't be able to tell that by just sort of observing these images, even if you would zoom in and spend some time on it, because yes, we can write domains. The domains in hafnium dioxide also have rather good-looking domain walls, and they're not very broad. If you look at the hysteresis loops, the evidence is sort of even more amassing. Both have square phase hysteresis loop. The amplitude hysteresis loop here is a little bit less defined than in PZT, But what I would like to draw your attention also is the sort of presumed coercivity in hafnium dioxide is as large as 5 volts, which is, so it's not a thin hysteresis of some sort. So, I mean, basically, without some extra explanation, there's no reason to reject that as non-ferroelectric. But in a few slides, I'll try to convince you that we can differentiate between these two quite unambiguously, and this is a ferroelectric, and this isn't in the ground state of the material. So this is a case of charge injection. There are no domains, there are no order parameters. That's, of course, assumption, but that's what the signal seems to tell us. And so they are quite different in terms of underlying physics. But to do this, I'd like to sort of guide you a little bit through this problem of the phase flip in PFM. So we have a vibrating cantilever, we're looking for the phase. So what's a phase flip? Well, phase flip is just the instance where tip motion changes direction, going one way or the other. And so, piezoelectricity has been called upon as a very efficient way to change the directional motion of the tip, because every time we switch, the piezoelectric sign, the piezoelectric coefficient, effective piezoelectric coefficient changes sign, and so the tip was expanding or going outside of the material in one case, and then it's going, or it was going in the material in one case, then after the switching, it's going out of the material. And so if we had access to this piezoelectric strain all the time, in fact, this talk probably wouldn't be necessary, because this is a very unique property of ferroelectrics and a very clean signature of piezoelectricity. And so in that case, it's very well defined. But the problem is that the signal here is typically not strong enough for us to just get them in mass. So what we do is we take derivatives of this loop using lock-in amplifiers. And then derivative of this will look like a nice square loop. And then we decompose it in sort of amplitude and phase, and the phase flips where the ferroelectricity flips. So this is all well, and we all understand that. But piezoelectricity doesn't hold monopoly on phase flips. Any other force that changes direction of motion of the tip will also flip the phase. And one such force that seems to be ubiquitous in these measurements is contact electrostatics, where you would imagine a tip that you bias, and so you put some charge on, and it interacts with the charges built in the material. Now, contact electrostatics by itself follows the same law that any electrostatically biased capacitor goes. The capacitor tends to squeeze in with a magnitude that's quadratic, scaling quadratically with the difference between the applied bias and the null potential. And so if you take a derivative of this value, by the way, in real experiment this is almost undetectable, but the derivative is very much detectable. What you have is a phase flip, but without any hysteresis. And the phase flips here when the DC bias compensates the built-in potential. So this is very familiar for those of you who have ever done electrostatic force microscopy, because that's, or Kelvin probe force microscopy, that's what actually the sort variable is there. And in contact it works almost exactly the same. And of course the derivative of this is a straight line with a negative slope, and the amplitude signal will look like a V sign. But unlike the piezoelectric signal, the definitive feature of electrostatics is that it scales linearly with applied DC potential. That's why we put emphasis on in-field observables. Moreover, electrostatics will become hysteretic in phase if this null potential starts to change during the experiment. And how does that occur? Well, you apply a lot of electrical bias to switch or to change the material, and it might inject some charges that will change the null potential very easily. And in that case, you have sort of a family of curves. And then if you're sampling at one potential remnant bias, let's say, you will have a very nice, clean phase flip. So basically, this is what the situation looks like. So in the hysteresis, they call it caused by polarization reversal, and by electrode behavior, so to speak, both have phase flips, but they have very different dependence on the applied DC bias, which in one case should not be strongly dependent on DC bias at all. Well, in the other case, you would have these sort of straight lines where the electrostatic force is scaling linearly with applied bias. And of course, we might end up having pure dielectric behavior where there is no phase flip and nothing's changing about the material. And in all realities, it's a mix of all three properties. So we actually implemented the protocol how to fish out the dependence of the probed volume on applied DC electric field. And I'll probably skip this slide, but the idea is that usually we do just one of these pump probe waveforms to probe the change of the material as a function of sort of right pulses. But now we're going to have a sequence. The difference between the sequences is that we change the value of the read bias. This is what the data looks like. This is an actual response of hafnium dioxide as a function of applied DC read. And what you see is just a sequence of straight lines. And remember that electrostatics is very strongly dependent on applied DC bias. So this signature alone immediately rules out ferroelectricity within the measured accuracy. And to sort of put this point more emphatic, so here's the comparison of this protocol on PZT and hafnium dioxide, and you can very clearly tell that even though these look very similar, these two behaviors look very dramatic. So this is dominated by piezoelectric hysteresis, which is not strongly dependent on the read condition, where in this case it's basic electrostatics response, and there's no ferroelectricity to be had within the measured accuracy. And there's actually a shortcut to doing this procedure. Just comparing sort of remnant hysteresis response to what you would get, which is what we call in-field response. So basically imagine measuring piezo response here on top of these and here, and then comparing them against each other also reveals a very dramatic difference between the two types of hysteresis, which looks weakly dependent on the procedure in PZT and very dramatically electrostatic in-field, whereas some weak response in the remnant response. So we can pretty much very clearly differentiate with this protocol or with this approach, or looking at the in-field variables, something that's ferroelectric from something that's not. But there's more to be had out of this exercise, because now we have actually access to the contact electrostatics, and it turns out to be pretty interesting. So first of all, we can reanalyze this data and extract the actual intercepts. How much do we change the null potential of the material? And it turns out this is the governing hysteresis in all of these parameters. Right? So you can see that the junction potential changes by as much as 2.5 volts as you cycle this material with applied right bias. And so this would correspond to a charge density of about over a few microcoulomb per centimeter squared. Interestingly, if you overlay this on a classic piezoelectric or PFM hysteresis, it will look almost identical once you scale them correctly. So we think we're on the right track. Furthermore, because we extract the junction potential directly, we can compare it to our favorite technique of electrostatic force microscopy, where we actually lift the tip from the surface, so they're explicitly sensitive to electrostatics. And we see that the range of potentials that we leave on the surface is very similar in contact versus non-contact. So minus 0.5 to 2.5 volts here, and this is minus 0.2 to about a volt. So there's actually sort of an internal mechanism to re-verify these measurements even beyond sort of the excessive evidence that things are on the right track. A somewhat more interesting property is that the slope of these lines also changes as a function of a voltage stress applied to the material. And what does that mean? Well, the slope of this line is related to the capacitance gradient. And with a little bit of modeling, we can actually derive that this gives us access to dielectric constant changes in the material. This will work primarily when the dielectric constant is low, so something like less than 20. But nevertheless, there's a pretty interesting range of dielectric constants where we could be uniquely sensitive to all of these new materials that are being predicted, weak ferroelectrics, improper ferroelectrics, where there could be other effects going on, or even materials that are explicitly non-ferroelectric. So finally, we can look at the charge relaxation rate, and here too we find something that could be expected, but it is very nice to sort of confirm that the charge relaxation rate from the material when the electrode is present, so in a capacitor, in a scale capacitor, is far larger than the charge relaxation rate when the capacitor is taken out. And so the way we explain this property is that if you think about the charge distribution that we create with the probe in the material, it will be localized pretty close to the surface. And if there is a metallic grounded contact still in contact with the surface, there's a pretty large probability for tunneling out of these trap sites back into the contact, and it relaxes the charge over time. Whereas in non-contact, because the film is fairly thick, the charge has nowhere to go, and so you create sort of a flash memory device. But there's something actually even more interesting to ask here is why are you able to put charge in the material to begin with? And this is a thing where these studies eventually will lead. Reappreciation of defect chemistry, if you want, of simple and more complex oxides. Okay, am I doing that time? Six more minutes. Okay, that's a small amount of time. Okay, so let me. So I'll have to go a little bit fast forward. We also looked very carefully in Strontium Titanate. I know it's been on the minds of a number of researchers. And again, this picture is very dramatic, so it shows very clearly that Strontium Titanate grown on almost lattice matched DSO is clearly non-ferroelectric, even though it gives ferroelectric hysteresis loops compared to PZT. But this material is TO and GO. That cannot be ruled out as non-ferroelectric. And so Then it got us an idea, so what if we look at the material that is polarizable but is not ferroelectric, such as BST? And here the trick is sort of going further deeper down the alley of in-field variables. So I just talked about electrostatics, but the other thing we want to consider is electrostriction in contact. And specifically, because we're looking at the derivative values, right, we will look at the derivative of the electrostatic signal, which is proportional to the dielectric constant. And so then Sasha suggested, well, let's throw in a very simple expansion for what the dielectric constant is going to look like as a function of polarization. Take the derivatives of it, invert it, and build sort of a simple model for what you would expect for sort of vibration of the tip that's excited in the presence of the polarizable material. This is not a very pretty looking expression, but it has several parameters to which we can directly feed the data, such as gamma, k, and beta. And what you see here is a simulated response that we expect to see from this film as a function of increasing parameter gamma. As you see on the next slide, gamma is actually proportional to, it is related to the dielectric tunability of the material. Lo and behold, the experimental data that we are observing looks quite similar. We had this sigmoidal shape of the response sometimes with the slope. And because the model decomposes into electrostatics and tunable part, with some reasonably, I would say, frivolous choice of fitting parameters, we were able to extract, we were able to fit these curves quite reliably. And this is really the main result of this experiment, is that we are directly extracting the tunability of the material, or the change of the dielectric constant in field compared to some random state, as a function of applied voltage, and we can map out these changes with a substantial resolution. It's a pretty interesting picture to consider. So what are these regions due to? So there's very little correlation between topographic contrast and these regions of increased tunability. So could they be some polar nanoregions, or could it be chemical inhomogeneities? We don't know yet, but the length scales are very interesting, and sort of doing temperature-dependent measurements of this would be interesting by itself. Another thing I wanted to mention is that we were able to verify this approach as well by doing a direct comparison between this PFM-style tunability measurement and microwave measurements, where you can see that microwave microscopy directly probes the capacitance under the tip, and so the inverse tunability comes out very close between the microwave, which is the red signal, and the PFM derived. So this approach really works. And finally, I have only 1 minute left or so. I will show you the strong evidence for ionically mediated hysteresis. So we have been interested in the approach to look at moving ions in the material for quite some time, with the basic idea being that if you displace ions out of any material, that material will change its volume. That's called the Vegard law, as we know it for a very long time, and it can be adapted to these local probe geometries, though with a lot of approximations. But the basic expectation would be that, yes, we should have some kind of vibration of the tip induced by ionic motion. By now, the theory has made a lot more inroads into this technique than experiment, because it's just the way things probably should work. There are a couple of things that are predicted for this technique of electrochemical strain microscopy. Number one is a very strong frequency dependence of the probed signal. And the frequency dependence here is determined by basically a characteristic length scale over which the ions can travel in the material. So it's proportional to the diffusion coefficient divided by some characteristic length scale, which could be the size of the tip, the size of the grain, and for every specific situation. And the other point is that these loops should not look like ferroelectrics at all. In fact, they should look like some oval shapes. They shouldn't saturate at all, and they're not very well differentiatable, so there's no microscopic reversibility in these materials, or in these systems. So when we look at the experimental signatures of PFM done on in this case it becomes ESM, I guess, done on lithium cobalt oxide and YZ, what we see actually is a picture that is not at all like the theoretical predictions, and this was very troubling for us for a very long time. And so now that we understand the contact electrostatics much better, we suspect that the contact electrostatics is responsible for a lot of these hysteresis. It doesn't rule out ionic motion, but the mechanism is quite different. However, I'm pretty happy to sort of show you this preliminary data that we have found a magic material on which we think we will be able to understand ionic motion much better. And this is a late ferroelectric copper indium P2S6. And what you see here is a direct strain loop. It's not a derivative loop, as a function of applied bias. And what's very interesting here is the length scale here, because as we apply bias, we can expand the surface volume by several nanometers. It's a colossal amount. But despite this large expansion, the material is fully reversible. In other words, we can pull the ions out and put them back in without seemingly damaging the material. If we do the imaging on top of this, we see that the reversibility is partial, but nevertheless it's the case. The reason why this is occurring is that copper indium P2S6 is a very happy material, a very lucky material for us. Its easy access, if you want, for ionic migration is very well aligned with our field gradient, and it has very clean, cleavable surfaces as any other layered material, and so we are working in the regime of good electrical contact. Which brings me to my summary that the question to switch or not to switch can be fairly efficiently answered with in-field observables. And if you apply these methodologies to PFM and answer yes, well, that's great. But if you answer no, it actually opens a whole new world of electrodes, relaxes, and ionics, where all manner of applied and then fundamental questions can be asked with nanoscale resolution. Thank you for your attention.
Thank you. So we have the full 5 minutes for questions. Thank you for staying on time. Yes.
So Peter, it's a very compelling argument about the use of the in-field. The example that you chose with regard to the hafnium oxide, and I'm sorry, I'm not privy to the discussions that happened in previous meetings here. Obviously, there's a lot of interest in the device community with hafnium oxide. Could you tell us how those are made
Yes.
in relation to what people are claiming
Yes.
For several years now?
Sure. Okay, you're talking about zirconium dioxide probably, right? Because I think zirconium dioxide was suspected to be, well, actually, hafnium dioxide, right? So we are collaborating with the group, I think in Germany, right? There was a first report that there might be ferroelectricity in there. So these ones, we're aware of these. And so, what is a good model system to learn how to do experiments? In complex fluxes, it doesn't exist. So this was ALD-grown film in, well, machine probably that looks very similar to what a standard ALD machine deposited on thermal silicon dioxide. So 10 nanometers, we've done a range of thicknesses, 20, 30 nanometers. So we tried to not introduce any extra ingredients that would create interesting prospects, but now in light of the fact that there could be defect-mediated ferroelectricity and whatnot, this becomes interesting. Nevertheless, John, I mean, for us, the point is that this material is definitely not ferroelectric because we cannot detect ferroelectricity in it. So it may be ferroelectric, and this is really the answer here. In fact, in copper indium P2S6, we can image the domain structure with PFM, but the contrast itself is fully electrostatic. So once we drop below 5-6 microcoulomb per centimeter squared, you're sensitive to other things that dominate, and ferroelectricity may be hidden somewhere, but it's below the noise. It really pushes us also to develop the noise limits because AFM has not really been developed in that sense for significantly, but that. Yeah.
Okay, are there any more questions?
Thank you. You mentioned strontium titanate on neorium galate and disco, and you obtained opposite behavior practically on, or opposite what is known in literature. Both systems should be non-ferroelectric at room temperature, but STO on dysprosium scandate should be ferroelectric close below room temperature. This is experiment at room temperature, right?
This is a room temperature experiment.
Did you try to measure, let's say, 40 Kelvin below? Or
We did. We also published a paper on it, and so we want
because
to go back to
there
this
are many
experiments.
experiments showing that it is ferroelectric. It is seen in phonon dynamics. It is seen in permittivity. Can
On
you
disco.
On disco, yeah.
And at what temperature?
270 Kelvin.
270 Kelvin. That's fine. So what we observed with both of these materials as we drop down to about 110 Kelvin is that we can very efficiently do the charge writing trick. So phase flips, domain walls, and whatnot. But the signatures very much remain, well, we haven't really done this level of analysis on it. So I have to, sometime within a few months, maybe I'll write, because we're trying to go back to a lot of the things that we have done in the past and really look what is dominating the signal. It may not be incompatible, right? So it may still be ferroelectric and we may still be sensitive to it through electrostatics. And actually, copper indium P2S6 will be a great model systems for us because it's exactly the material with 5 microcoulomb per centimeter squared. And so it could be that we are electrostatically sensitive to things that are ferroelectric. Every time you flip polarization, you will also change the Nolan potential naturally. And so in this case, this is why I guess my disclaimer was on the hafnium dioxide slide, right? So it's in the lawyer definition of things, it's only within the accuracy of this experiment. But our very first conclusion, which we did in 2010, was that with strain, the CO becomes ferroelectric, and we can see it through a combination. SHG was dominating that work, but PFM showed contrast that could be stabilized at low temperature.
Okay, let's thank the speaker once again.
Thank you.
So the last talk in this session is by Massimiliano Stengel, First Principles Theory of Flexoelectricity.
Excellent. Yes. Okay. Good afternoon, everybody. Let me set this up. My name is Massimiliano Stengel from Barcelona. This is something unexpected. No, I don't want this. Okay, this is better. Which one is which? Okay, this is the pointer, right? No. This one is the laser? Uh-huh. And this is for the slides?
That probably is for the slides. I'm not.
Okay, excellent. I'm Massimiliano Stengel from Barcelona. I would like, first of all, to thank the organizers for inviting me here. It's great to be back to this conference after a few years. I'm going to talk today about flexoelectricity. And in particular, I'm going to tell you a story about the advances in first principles theory that have brought us in the very past few years, essentially from a pioneering stage, to the point where you can calculate not just the polarization, but the full electronic structure response to a complex deformation like a strain gradient. What I'm showing you here, I'm not sure I got this actually. What I'm showing you here is what happens if you bend a slab of strontium titanate like this, and if you look at the band structure projected along the bending, along the normal to the surface, and here you get the tilt in the conduction band edges at the bulk level, and you get surface effects and everything you can need to completely define the electronic state, the electronic response of this system to bending. But before I tell you about this, let me tell you the whole story from the beginning. So I'll start to tell you first what is flexoelectricity, what is useful for, and what are the techniques we had to develop to calculate it. So essentially, flexoelectricity is a close cousin of piezoelectricity, which you're all familiar with, which is the response of a system to a uniform strain. If you take a slab and you compress it in plane, uniformly you get a polarization out of plane. But the thing is that you need a functional material, of course, that breaks inversion symmetry, because a strain itself does not break inversion symmetry. So it doesn't work for any material. Flexoelectricity is a very similar thing in that instead of compressing the slab or applying a uniform strain, I apply a strain gradient, which in this case is a bending deformation, which means that I'm actually, I'm really struggling with this. Essentially here I have a gradient of the transverse strain across the slab normal, and this induces a polarization in any material you can think of. You can take sodium chloride, you can take paraelectric material, and just because the strain gradient has a direction, it breaks inversion symmetry and induces a dipole in any material.
why don't we have yet a flexoelectric device? Well, the main drawback is that this effect is negligible in microscopic objects. And only in the past few years, with the advances in preparation and characterization of nanoscale structures, the research took off on this front. And actually, people realized that this effect can be large at the nanoscale, where strain gradient can be massive. And so, not only it is important for the fundamental behavior of thin films and anything you can think of at the nanoscale, but it's also something that can lead to some useful functional properties. The first idea is of course to use it as a substitute for piezoelectricity. The idea is simply to take a non-piezoelectric material, and instead of making it a cube, you make a pyramid that breaks inversion symmetry by shape. This produces a strain gradient when you compress it, and so an effective piezoelectric coefficient of this composite, which is mediated by flexoelectricity. But of course, flexoelectricity depends on the strain gradient tensor, which has a different symmetry than the strain tensor. And so this leads to many new functional properties in that you can use it to rotate the polarization in thin films. Actually, this is a thin film that has formed A and C domains, and you have huge strain gradients because of the elastic matching with the substrate, and there are also some polarization patterns that has been interpreted as a consequence of flexoelectricity. Or you can use it to, for example, to make a nanotypewriter, like in this example, where you have a barium titanate film and pressure is applied with the AFM tip to switch nanodomains locally, mechanically, and so possibly store information on the film just by mechanical means. Okay, in order to we want to make to exploit this effect in devices possibly, and so we need to understand it at a very fundamental level. And the thing is that so this is a list of publications that is essentially the theoretical background of this talk. And as you see, apart from two papers here, which are seminal works that establish the conceptual basis of what I'll be telling you about, the real ab initio works, let's say I call them real because I'm an ab initio theorist, but it's not, I'm not intending to say anything bad about the earlier approaches. It started really in the past 5 years with the work of Hong and Resta and Vanderbilt, who are here in the audience. So this is very recent and still not yet complete, in the sense that there are still some aspects of the theory that are problematic to treat in a first principles context. And in particular, it is not easy to get all the components of the flexoelectric tensor. It's not yet implemented in an ab initio code. So you have to do a lot of complex calculations and post-processing to do these things. And also there is an issue about the surface contributions, which are predicted to be important. And there is little, when this work started, there was little knowledge about what they look like, how they affect the response of a finite sample. So I'm going to essentially focus on these two aspects, essentially how to get all the components of the bulk flexoelectric tensor and how the surface effects enter in the theory and why this is different from piezoelectricity. So let me start with the strain gradients. The simplest case you can think for a strain gradient is a one-dimensional rail where you have essentially only one displacement direction. And so we have only one component of the strain gradient, which is essentially a quadratic pattern where the atoms displace from their equilibrium position as x squared. And this produces a linear increase in the lattice parameter along the only direction we have. When we go to 3D, this becomes a nasty third-rank tensor, which can be written in two different ways. Essentially, you can take the displacement field and take a second derivative of the displacement field, or take the symmetric strain tensor and take a gradient of the symmetric strain tensor. Actually, the two are not connected on a one-to, well, they are equivalent in the sense that there are 18 components here, 18 components here. So one can establish a one-to-one relationship between the two and use one or the other representation depending on whether I'm doing calculations or I'm talking to an experimentalist, essentially. This is more intuitive because you're used with the concept of to the concept of the strain tensor, and so it's easy to figure out what is a gradient of the strain tensor. And I'll be using mostly this representation in the rest of the talk. So there are 18 components, and this sounds like a big problem to represent on a piece of paper, especially. But fortunately, in cubic materials, which is essentially what this talk will be about, we have only 3 independent components of the strain tensor, and all 3 can be easily represented on a 2-dimensional sheet. So you have the simplest one, which is the longitudinal strain gradient, which is an increase of the longitudinal component of the strain tensor along one direction, is equivalent to the 1-dimensional example I showed you in the previous slide. Then you have the transverse component, which is the bending deformation I showed you at the beginning. And then you have the shear component of the strain tensor, which looks like a transverse acoustic phonon. And this time is an increase of the shear component of the strain tensor along the horizontal direction. So these are the only 3 components we need to worry about for the simplest class of material, which is, for example, cubic strontium titanate, which I'll be calculating later. So how does all this produce a polarization? There are 2 contributions. One is from electronic effects, just like the piezoelectric coefficient. And for the electronic effect, you can think of an orbital sitting on a given atomic site. Within a strain gradient, you have a variation, a linear variation in the distance between the sites. And so this creates a broken symmetry environment for this orbital that deforms and actually produces a dipole. And then we have lattice-mediated effects, which depend on the interatomic constants of the lattice. For this effect to happen, you don't need actually Born effective charges or a polar material. You can have it also in silicon or in covalent semiconductors. Here, you do need actually at least a partially ionic solid. Because you have atomic displacements, and these atomic displacements, to create a polarization, need to have a charge attached to them. So this is very hand-waving. The goal is to calculate all this from first principles. And we have a very big problem from first principles, because translational symmetry is broken by a strain gradient. So at first sight, we cannot use periodic boundary conditions, Bloch theorem, plane waves, etc., etc. We need to find a different way to proceed, and this is essentially what this talk is about. And the idea is to take this non-periodic perturbation and make it at least quasi-periodic. So instead of having a macroscopic strain gradient, modulate it in a sinusoid. And so you create essentially an elastic wave, an acoustic phonon. And in this case, you can see that if you take a snapshot, you recognize a longitudinal strain gradient here and a shear strain gradient here. What do you do with acoustic phonon? You take essentially a Taylor expansion around the gamma point. This is the long wave technique. And if you look at an acoustic phonon, you see that at order Q0, you have essentially a rigid translation of the whole crystal lattice. At order Q1, you have effects related to strain, which are concerned by piezoelectricity. And finally, at a second order in Q, you have what we're looking for, which is the strain gradient effects and therefore flexoelectricity. So we have essentially to do a second order perturbative expansion of whatever property you can think of an acoustic phonon around gamma. What are these properties? What do we need as a property to calculate the flexoelectric response? Well, the first thing is actually the acoustic phonon eigenmode, so the atomic displacements that are associated to the acoustic phonon. Of course, these displacements are trivial if you consider only the gamma point, but if you move away from the gamma point, the acoustic phonon increasingly mix with the optical modes, and you have these so-called internal strain tensors, which relate at first order in Q to piezoelectricity, and at second order in Q to lattice-mediated flexoelectricity. And then, once you have these atomic displacements, is not enough, because you need actually something that couples the displacements to the polarization. And for this, the idea is based on Martin's theory of piezoelectricity that consists in looking at the charge density response to the displacements of individual atoms. So you imagine the infinite crystal lattice, you displace one atom, this will induce a perturbation in the electronic charge, and you analyze this perturbation by expanding it in multiples. At order Q1, of course, you have the Z star, the Born effective charge tensor, which is essentially the dynamical dipole induced by the atom. But for electromechanical effects, you need actually to go to higher orders in the multiple expansion. You need to consider the quadrupole, and for flexoelectricity, the octupole. Let me focus on the hardest part from a theoretical point of view, which is the electronic contribution. And for that, we discard for the moment the internal displacements of the atoms in response to the strain gradient, and we just look to a purely elastic wave, and we see what is the polarization induced by this frozen ion phonon. So this was the breakthrough of Richard Martin's paper in '72, which was to write the piezoelectric tensor, the frozen ion contribution to the piezoelectric tensor, in terms of the quadrupolar response to atomic displacements. And actually, you have this formula that relates this frozen ion tensor to these quadrupoles. And actually, you can see that if you look at the symmetry of these tensors, you see that they have the same number of independent components, and they can be inverted. So if I know the quadruples, I know automatically the electronic piezoelectric tensor. So the idea that was initiated by Raffaele was actually to go for flexoelectricity to look at the octupoles, which is the next lowest order in the multipolar expansion. And indeed, you do have a relationship that connects the frozen ion flexoelectric tensor to these electronic octupoles. But the situation is not as fortunate as in the piezoelectric case. You cannot invert this equation because mu has more information than the octupoles. And so we have some components of the flexoelectric tensor that we cannot directly access simply with the knowledge of the charge density. We need, in principle, to look at the polarization that responds to an atomic displacement, but this is something that we haven't implemented yet. So we need to look for a sort of workaround this problem. And the idea I had is to work, instead of taking the bulk system, to work with a slab vacuum supercell and do the same kind of long wave analysis, to look at the macroscopic deformations of the slab supercell and take the same set of elementary deformations. Why do I use this strategy? Well, the surface charge is in principle related to the bulk polarization. So if I know the surface charge, then I will probably can reconstruct what was the bulk contribution to the flexoelectric response. And then, if I have a cubic material, I only need to consider only one type of deformation because, as I told you before, some information can be gathered at the bulk level from the octupoles. So I do the octupoles, I have these two equations, I put this third number I plug the third number here, and so I can resolve the three components fully. So then, at this point, I have a small technical issue, which is how to bend a first principles code, which is notoriously hard to make. Is not very flexible. Essentially, the thing is that even to represent what I mean by charge density or by an electric field when I deform a piece of material is not trivial, because essentially, if you calculate just the difference between the charge density before and after the deformation, you don't get what you would like, because essentially the material has displaced from the original position. If you just take the difference, you don't get anything close to something periodic, for example. So we need actually to do something in order to find a correct representation for these response functions that need to be microscopic. So the solution essentially is to combine the long-wave acoustic phonons I told you before with coordinate transformations to define these quantities in a sort of frame that is compliant with the deformation. And this is actually a natural approach, because you can think of a deformation as a 3D mapping from the unperturbed system to the final state. So a function that essentially goes from R to R prime. And then we don't need to worry about where the material has gone, but we just need to calculate the linear response to an inhomogeneous metric. So the example is something like this. We take an acoustic phonon, and we can represent it two different ways. We can think of it as atoms moving in a fixed Cartesian frame, which is defined by the straight lines here. Or we can actually think of it as fixed atoms that do not move, but actually the coordinate system itself is displacing. And this defines the deformation. So we have some issues then with the electrostatics, because we need to work in a curvilinear frame. And for this, actually, general relativity comes in help. In particular, I took inspiration from transformation optics to be able to solve the Poisson equation in a system that is no longer a Cartesian. And it's actually easier than it sounds. And actually, you just need to consider that the vacuum permittivity becomes a metric-dependent tensor, and otherwise, you can just work as if you were in a rectilinear space. And this these techniques have been used to design invisibility cloaks via coordinate transformation, which is essentially to deviate light rays around an obstacle. Okay. How am I doing with time? One more minute?
No, 10.
10, okay. That's better. Okay. So we solved the issue about methodology, which sounded pretty hard, how to bend a slab supercell and calculate the microscopy response. Now we have a problem that is more rooted in the physics. So we are used to the surface theorem that tells us that the bulk polarization is equal to the surface charge. But a strain gradient breaks periodicity, so we need to be careful about how we use concepts that are valid in a periodic context. And so we need to, and in particular, this relationship is no longer valid in this case, but as we see in the following, it is valid in these two cases, which is the ones that we need to worry about if we want to bend a slab of a given material. So I won't be discussing about this, which is a bit too long for 9 minutes. Okay. So the issue of the surface response. Why do we need to worry about the surface in flexoelectricity? So it is instructive to look at how a slab responds electrostatically to a deformation. And for this, I like this model by Tagantsev and Yurkov, where they consider actually a sandwich of a material that is inert in the middle and has two piezoelectric layers stuck on top and at the bottom in such a way that the system is centrosymmetric. So the piezoelectric coefficient at the top is opposite to the one at the bottom. Why is this model useful? Well, because any surface of the most symmetric material actually behaves like this, because the surface breaks inversion symmetry just because the bonding environment is truncated, so it does have a piezoelectric response near the surface. And this you can represent this way. If the slab is centrosymmetric and you strain it, you will have an electric field in the surface region on one side and an opposite dipole on the other side in such a way that the overall response to a uniform strain cancels, just because the system is overall centrosymmetric. And if you look in terms of the induced potential, you see that a uniform strain, essentially what it does is it changes the depth of the quantum well that corresponds to the slab. So you change the surface dipole, and the average potential inside moves up or down with respect to the vacuum level. But this does not produce an overall electrical response because the slab is symmetric. When you do a strain gradient, for example, a longitudinal or transverse one, what you have is that the local strain is opposite at the two ends, is not equal as in the previous example. So the contribution of surface piezoelectricity actually sums up here because you have a minus sign here that makes the two dipoles produced by the surface point in the same direction. And then, in addition to this, you have a contribution from an induced electric field within the material, which is always flexoelectric at the bulk level. And the result is this: from the point of view of the induced potential, there is a constant macroscopic field inside the material, and there is a variation in the surface offset here and here, so that you have this broken line that gives you ultimately the total open circuit voltage induced by bending. So the main thing to understand here is that the surface piezo scales identically to bulk flexo. So this means that if I take even a macroscopic surface, the overall response will be sensitive to what is the atomic nature of the terminating layer. And then this is also has a comforting message in that it says that the surface effects essentially concern only this region, which is close to the surface, while in the bulk, the internal field is indeed a bulk property. So I can use this technique that I showed you before to infer the bulk tensor from a slab calculation. Okay, let's go to the results. We went through the theory. We're all alive, I hope. So essentially, I wanted to show this surface dependence. So I took two slabs with different terminations. One is a Strontium Titanate slab with an SRO termination, the other with a TiO2 termination. I will consider these two type of strain gradients full atomic relaxation, and I will look precisely to what I said before, to the overall flexo voltage coefficient, which is the offset from one side to the other upon bending the slab. There is one little detail to remember when we do strain gradients, is that when you apply a strain gradient deformation, there is always a secondary strain gradient that appears because of the elastic equilibrium condition. For example, here, if I do this kind of deformation, I pull the surface region on one side and I compress it on the other. So because of the Poisson ratio, I will have simultaneously a longitudinal strain gradient, and the result will be the sum of the two if I relax the whole structure. Computational details, please ask me later. And then I have the main result. So I take a Strontium Titanate slab and a TiO2 slab, and the result is this number for the two. So you see that indeed the internal field is a bulk property, but the surface, the influence of the surface is so large that actually it can change the sign when I go from TiO2 to SRO. And so actually the surface has a dramatic influence on the response of an STO slab to bending. So this was the 5 minutes? Okay. This was the result. So we can go back to the slide I showed you at the beginning. So we have the Strontium Titanate slab. And actually, here I showed you something that is that is not very interesting from a physical point of view. This is the macroscopic electrostatic potential inside. But from an experimental point of view, what I want to know is actually what will do my charge carriers when I bend the slab. So essentially, to go from the macroscopic electrostatic potential to the band structure, we just need to add the deformation potentials to the macroscopic electrostatic potential. And so this way, we can build a complete diagram of the electronic response of the system to a deformation. And this is a summary of what I showed. We have a tilt of the conduction band, a tilt of the valence band. They're not equal, which this points to another fact that is quite remarkable in the case of flexoelectricity, and that sort of challenges the interpretation of this phenomena, is that the macroscopic internal field in a flexoelectric, in the flexoelectric case, it depends on what I choose as the reference to define it. So it is different if I look at the conduction band or at the valence band or at the electrostatic potential. So I must be careful what I mean by electric field when I do macroscopic modeling of these effects. And then this ambiguity actually disappears when I add the surface contribution, so the total dipole upon bending is always well defined. Okay, these are the conclusions, which is essentially what I just said. These are a few references, and I want to point out that there is actually, if you're new to the field, actually this is a very good starter, I think. It's a chapter we wrote in a book summarizing all the developments in the last few years. So please have a look if you're interested. And thanks for your attention.
Thank you. So we have time for some questions. I had a couple of questions. I didn't quite follow all the turns in the theory, but if I'm trying to understand how much is just sort of implementation issues that you didn't get to. In principle, you could calculate these octopole terms, I understood.
Yeah.
And if you did that, would you have needed all this other discussion about the surface and the bulk terms? Would that come out automatically if you could calculate?
Actually, with the octopoles, if you work at the bulk level, you get the two components of the octopole tensor. In a cubic material,
I see what you're saying, yeah.
You have just the longitudinal octopole, and then you have...
Let me say it the other way. Could you calculate the tensor directly by using the method of long waves for those higher order tensors?
Well, you can calculate the octopole, all components, but this does not give you the full information for the flexoelectric tensor. For that, you need one more component, which is not... was that your question?
I think so.
So this whole thing about the surface and the surface charge was to try to use the charge in a slab case to infer something that actually you need the polarization to understand.
Need to maybe ask a little bit more precisely. Could you eventually get the answer without ever doing a slab calculation? Could you just do some sort of a bulk calculation?
For the moment, no. It's not yet available. Ideally, yes. Ideally, yes.
Yeah.
Or if you had everything implemented, then you need a sort of microscopic theory of the polarization response to some perturbation, which is not. But in principle, once it is implemented, the bulk tensor can be calculated at the bulk level. But then you still have the problem of the surface, which if you want to calculate the total response of a real system, of a finite system, then you need also the surface contributions. And these are surface specific, so you do need a surface calculation. It depends on the termination, it depends on the chemistry at the interface.
Okay, are there any other questions, David?
Just for fun. So if a gravitational wave passes through a dielectric medium, does it generate a polarization wave?
Well, I thought about it, and I think yes.
Okay.
Did they find a gravitational wave?
Okay, I think we need a break. So let's thank the speaker again. So I didn't want to ask him that question. That band structure you showed and sort of the schema. That's something you actually calculate then using the slab calculation. Can you actually exhibit a band structure presence of long wave acoustic phenomena?
Yeah. Yeah. But it's not a direct calculation, of course. I do not calculate a band thing. It's all. Sure.
Okay.
Sorry. It's all linear response calculations on a slab, one by one, slab sequence.
Right. Okay.
And it's all a matter of those levels and this is the level of the slab and everything together.
I'll look at that.